Okay, so this video is going to go over the Michaelis-Menten model. So let's go over it. So we have enzyme plus substrate combines into the enzyme-substrate complex. So going forward, we have K1, which is the rate constant for the forward reaction. And then we have K minus 1 for the backwards reaction, when the enzyme-substrate complex can dissociate back into the enzyme plus substrate. We also have the forward reaction from the enzyme-substrate complex into the enzyme end product, and that's shown as K2. Now, a very valid question would be, why isn't there a K minus 2? And that's because the initial velocity is measured at early times, so no reverse reaction is happening. So its K minus 2 is approximately 0, and that's why we don't have the K minus 2. Another thing to note is that K2 can actually be shown as K cat. So if you see K cat, that's the same as K2. So why is all of this important? Why do we need to know about this model? Well, so if we have this hypothesis, right, that this is how enzymes work, we want to see if a real-world enzyme would behave like this, right? And so if it did, then we can show it experimentally. We'd have to show it actually experimentally to show that this model is indeed how enzymes work in the real world. So how do we do that experimentally? Well, we can look at the kinetic behavior of enzymes, right? We can see how the substrate concentration affects the rate. And we also want to know what rate law the enzyme follows, right? So we have to find all this experimentally. So what we need is equations to represent real world stuff so that we can substantiate this hypothesis. So this only applies to steady state kinetics, where the rate of forming enzyme substrate complex equals the breakdown of enzyme substrate complex, right? This is important, and I'll get to that when we go over the Michaelis constant. Okay, so let's go over this. So V0, right, what we designated over here, V is the initial velocity of the reaction. So we can put up this rate constant of V velocity equals K cat, remember K2, multiplied by the enzyme substrate complex. So the max velocity is when all enzymes are bound to substrates. So let's talk about that, right? So what does that mean? So that means that the total number of enzyme, or when all substrates are bound to all enzymes, that equals the total number of enzymes, right? That makes a lot of sense, because if all the enzymes were occupied, well, then it would have to equal the total number of enzymes present. So Vmax is equal to K cat, remember that's K2, multiplied by the enzyme total. So why is all this important? Remember I said that this is all important because we need formulas, we need equations to show that that hypothesis was true, right? And so another thing is why we have to do all the derivation that I'm about to show you is because instead of using ES, right, because over here we have ES, that's a lot harder to measure than using substrate concentration and enzyme total. These two we can definitely measure experimentally, and that's why we're going to use these and find a rate law or formula that can, or equation that can help us rather than using ES in the equation. So let's go over the Michaelis constant derivation. So we have enzyme plus substrate equals the enzyme substrate complex, right? And K1 going this way and K minus 1 going the other way. And then the enzyme substrate complex, K2, and then E plus P, which is just enzyme end product. So this is why this model only applies in a steady state kinetics where the rate of forming ES equals breakdown. And so this is how we make this assumption, because K1, remember, is this forward reaction. So we have two reactants, so it's going to be the concentration of enzyme, concentration of substrate. And then over here we can equal it because we're assuming this steady state kinetics. So over here we're going to do K minus 1, and remember in this one it's the backwards reaction, so the reactant is still ES. And over here it's the forward reaction, so it's so the reactant is still going to be ES, and then you have K2. Okay, so the first thing we're going to do is pull out ES, right? And so we're going to because it's present in both of these, and so we're going to pull that out, and now we can just multiply it by K minus 1 and K2, right? And then leave the left side alone, and then what we're going to do is divide both sides by K minus 1 plus K2, right? And then after that, we'll do 3 steps to get right here, right? So what we'll do is we will multiply k minus 1 plus k2 on each side to get the top portion. Then what we'll do is divide each side by k1 to get the k1 down here. Finally, we will divide each side by es, and so over here, right, you'll get es on the bottom. So that's 3 steps in one. And from there, that's how you can designate all of this as km, right? Because you don't want to have to write all 3 of these units every single time. So a shortcut is that they devise that km will represent all of this, and this is called the Michaelis constant. So I'll talk more about the Michaelis-Menten equation in the next video. So thank you for watching, and I hope this helped.